On this part, we're going to spend a bit of time exploring coordination chemistry. And first of all, let's start with some definitions. When you have a central metal ion, which is bonded to a group of molecules or ions, we call that a metal complex. And it can be a neutral molecule, or it can be an anion or a cation. And if it's an ion, we call it a complex ion. And when you have a compound that contains a metal complex or more, then we call that a coordination compound. So for example, in this slide, you've got a cobalt complex ion formed with a cobalt atom in the middle and 3 ammonia molecules, which are the ones here, and 2 chloride anions. And the whole structure is charged, it has a positive charge, so that would be a complex cation of cobalt. And if you had this as a salt, let's say for example we had the chloride salt of this complex, then we would have a coordination compound. Besides the metal ion that makes the center of our coordination compound of our metal complex, the other very important part of a complex is the ligand. And ligands are the molecules or ions that coordinate to the metal ion. And it comes from Latin, ligare, which means to bind. So they are usually anions or polar molecules. So they can be anions or they can be neutral molecules, but with certain polarity. They must have lone pairs to interact with the metal ion. They must be Lewis bases. And all the examples I've got in this slide, you have the molecule of water, the molecule of ammonia, and 2 anions, the cyanide and the chloride anions. And they all have those lone pairs, and some of them have also a negative charge, they are anions. Coordination chemistry started with a mystery and started taking our interest, the interest of chemists in the 19th century. And it all started with something we didn't understand. How, when you have a salt or a series of salts and they have the same metal and the same ligands, even in different proportions, they would have different colors. And we've got here the example of compounds that were originally formulated that appears in the table, like copper chlorides, cobalt chloride, sorry, with different molecules of ammonia, 6, 5, 4, and 4. And they had different, first of all, they had different colors. And that was quite peculiar in itself, because how could 2 compounds that allegedly have the same formula have different colors? And also, even if they all have 3 chloride ions in that formulation, when those compounds were dissolved in water, they liberated a different number of chloride ions per formula unit. And that again was quite a mystery. How could 4 complexes that have the same number of chloride ions in theory, when they are dissolved, not free those chloride ions, not free the same number of chloride ions? And the additional mystery of how could 2 compounds that have the same formulation have 2 different colors? How could they be 2 different compounds when they both had a cobalt ion, 3 chlorine atoms, and 4 molecules of ammonia? Werner put together the first theory that tried to explain this mystery. So in the late 19th century, Werner suggested that metal ions had 2 valences, a primary valence and a secondary valence. And the primary valence is what we call the oxidation number. So copper 2, chromium 3, etc. And the secondary valence was the number of atoms that were directly bonded to the metal. And he called that the coordination number. So 2 different things. One was the metal oxidation number, which was 1, 2, 3, etc. And the other one was the secondary valence, the number of atoms that were directly bonded to that metal ion, the coordination number. So when you look at together the central metal ions and the ligands that are directly bonded to it, you call all that makes up what we call the coordination sphere of that particular complex. So for example, in this cobalt ammonia ion we have in the slide, there is 3 is the oxidation number of cobalt, but the secondary balance is actually 6, because you have 6 atoms, in this case 6 nitrogen atoms, directly bonded to the cobalt ion. So the primary balance would be 3, the oxidation state, and the secondary balance for this case would be 6, the number of ammonia molecules, the number of atoms directly bonded to that cobalt metal ion. Werner's theory could explain why compounds that allegedly had the same formulation or very similar one, and they had the same components, could have such different properties like color or the number of anions and the type of anions that were liberated in solution when you dissolve those compounds. If you look at the example in the slide, you have here 2 compounds of cobalt with chlorine and ammonia. The oxidation state, the primary balance of cobalt, is the same in both. This is cobalt 3+. The oxidation state is the same, and the coordination number is the same. The number of atoms bonded to that central cobalt, in both cases, is 6. There are 6 atoms directly bonded to the metal ion. So both the oxidation state and the coordination number is the same. However, the coordination sphere is different. In the case at the top, there are 4 nitrogen atoms, 4 ammonia molecules, and 2 chloride anions attached to the cobalt. And in the second one, it is 6 molecules of ammonia, 6 nitrogen atoms attached to that cobalt. So same primary balance, same secondary balance, same coordination number, but they had a different coordination sphere. From Werner's theory, we learned that there was a better way of formulating these compounds. The original formulation did not distinguish between the atoms that were directly attached to the central metal ion and the ones that were outside, that were not part of that secondary balance, that coordination number. So instead of the original formulation, the modern formulation takes into account that all those atoms around the central atoms are different. You have some that are directly attached to the metal ion, that are part of the coordination sphere, in this case of the cobalt, and you put those in brackets. And then outside those brackets, you put the free anions. The anions that are part of the molecule, they are part of the compound, but they are not directly attached to the cobalt. They are not part of that coordination sphere. So when you dissolve that compounding, those will dissolve, will dissociate, and be free in the solution. And that explains why all these cobalt, chlorine, ammonia compounds have a different number of chloride anions free when they are dissolved, because in this case 3 of the chloride anions are outside the coordination sphere, and in this case there are 2 of them, and in those 2 cases only 1 of them is outside the coordination sphere. The others are part of the coordination sphere of that cobalt. Werner's theory could also help us predict why there are actually 2 forms of this compound of cobalt 3 chlorine and 4 ammonia molecules, because those 2 chloride of those 3 chloride anions, 2 are part of the coordination sphere of the cobalt, and they can be in slightly different places. They can be next to each other, and then you have what we call the cis isomer, or they could be in opposite, pointing towards opposite directions, and then you will have the trans isomer, and they would interact different with light. They would absorb a different amount of light, different frequency of light. They would have a different color. So Werner's theory could also help us understand or pointed out the possibility of isomers in this world of coordination compounds.